Okay, we'll go ahead and get started. We're not going to have discussion today. I just want to, at the end, I'll ask you guys, or you guys can ask me questions. So we're just finishing up visual imagery, and then we're going to do our review for the third exam. So a lot of you have your papers due tonight, midnight. So hopefully you've made good progress and you're ready to follow through with that. And then we can ask questions about that in the end. Okay, so this is about where we left off last time. Remember, we're talking about visual imagery and sort of the overlap between imagery, visual imagery, or mental imagery, and your perception of real stimuli. So if you remember, there's sort of a controversy if there's really a lot of overlap between these two things. So seeing the image and then just imagining that you saw that image. So this is one study, transcranial magnetic stimulation. So this is a process by which you can create an artificial lesion. Like, remember, we learn a lot from lesion studies, like having areas of the brain that are not functioning. We can kind of see if some performance is affected by that, not having that functional region, that means that contributes to whatever behavior you're trying to study. So in this magnetic stimulation, they created a lesion in visual areas and asked people to have mental imagery to remember certain things. And there was an effect on sort of the reaction times. So the conclusion is there is some real overlap. It's not just that prepositional thinking, if you remember back to the beginning of the chapter. We see things visually in our mind the same sort of way we would be perceiving an actual image. Again, it's more brain lesion type stuff. When you're missing sort of areas of the brain or visual areas, there are effects on your ability to have mental imagery. So in this case, a participant who lost part of their occipital lobe, it looks like, which deals with visual processing, they would imagine this image of a horse. And they could imagine the image of a horse, but we kind of talked about that spillover effect. So like when you imagine an image so close that you can no longer see the boundaries of it, you're so close that you're only seeing, the color of the horse rather than the outline of the horse. So people who had this injury, they perceived basically that overflow occurring at a further distance. Basically, they were less able to imagine the image closer towards them. So you can kind of see here just the representation. Seeing a horse at 15 feet might result in that spillover, or that's the total boundary edge, versus 35 feet for somebody who has damage or removed parts of their visual cortex. So there's also, this again speaks to that overlap and the functionality of perception and imagery. So this is, I think, another person, it's described in your book, remembered this area, this map of an area where they lived or where they were very familiar with. And when they had some problems with their visual cortex or their brain in that type of region, it did affect how well they were able to remember this mapped area where they were used to navigating. So again, speaking to that overlap and functionality, other things include people who have lost the ability to see color, so some kind of brain damage affects their ability to actually perceive color, will affect that ability to imagine color. So they also can't imagine color when they can't see color. So again, some overlap there, what you can see and what you can imagine. And also people who have some kind of image or some kind of damage that prevents them from seeing one side of their visual field. So say you can't really see your left visual field. If you're imagining mental imagery, you also have that effect in that side of your brain, or in that side of your visual field in your imagination. And here are two different lesion studies, or two different brain damage studies. So illustrating that even though there is some overlap, in this case you can see that there's some differences between them. So in one case, RM had had suffered a brain injury. I'm not sure if it was disease or whatnot, but the damage occurred in his occipital and parietal lobe, so areas associated with processing imagery again, and he could see an image in front of him and sketch that image that was in front of him, but he wasn't able to sketch anything from memory. So if an object wasn't in front of him, he couldn't imagine and then sketch it. And he also had problems verifying if a sentence made sense, that kind of thing. So in RM's case, his imagery was poor, but perception of objects, since he could still draw the thing that he was seeing in front of him, that was still okay. Whereas in contrast, you have CK, who was described in your book a little bit, I guess a graduate student who was hit by a car and had different types of injuries associated with that, brain injuries associated. So the perception of things in the environment was impaired. So he had problems like seeing something. It's a picture of like a feather duster, and he couldn't identify that it was a feather duster, had no real ability to identify visual imagery, but was able to draw images from memory okay. So again, even though they're really overlapped in these functions of perception, of perceiving the actual image and imagining the actual image, there are some differences. We can see that in some of these lesion studies. Okay, so here's sort of a visual representation of that information that was just presented, those two lesion studies. What it sort of shows you in that case. So you have the perception of an actual object from your eye. Remember all the light rays hitting your retina and being changed into energy that your brain can understand. So that's all brought in, that's perception. So you have visual receiving areas, then you have that higher level of processing the image and eventually storing your knowledge of the image in your memory. And then in the same case, or backwards sort of, you can see the line coming from your memory and going to the perceiving or the thinking of the mental image. So perception is located in both the lower and the higher visual cortex, and imagery seems to be located mainly in the higher visual centers. So you don't necessarily need that ability to, or it makes sense, you don't need your eyes to work to be able to mentally represent mental imagery, or ears, or whatever you're talking about in that situation. So basically, there's still differences between the two things. We see that there's some difference between the two things, but some people aren't totally convinced about what specifically differs between those two things, different scientists. So most evidence suggests that imagery and perception are closely related to each other, but the manipulation of mental images is harder than the manipulation of visual images. Sort of makes sense. If you're thinking about something instead of really seeing it in front of you, like imagine changing sort of the image of the rabbit or drawing that from memory versus drawing that from what you're seeing in front of you. It makes sense that we have that limited capacity sort of to represent totally that image unless you have like a photographic memory. It fades quickly, so it's hard to remember everything that was going on in the scene and therefore harder to figure out what to do with it if you're just imagining it. And then just quickly, tricks to help you remember things or ways that we can illustrate improved memory through sort of this process of visual imagery. So this study is described in your book. It's kind of interesting. Items are remembered better if they're interacting with each other. In this case, these 4 images were presented to different participants, and basically you test who remembered things better. So there's the normal condition, and then there's the strange condition, or bizarre, I guess it's called, and then there's the interacting and non-interacting. So you can see the upper left, you have a piano and a cigar, totally normal. The upper left, or in the upper right, you have a weird piano falling apart and a cigar burning at both ends. So totally bizarre two things that are strangely presented to you. And then in the bottom, you see the two images, or you see the two objects in the picture interacting with each other. So on the left, you have a cigar on a piano, and then in the right, you have a piano smoking a cigar. So what was basically concluded is that even if they're not bizarre, the interaction lets you remember them better. So one might think that having things strangely, bizarrely connected to each other, so that piano smoking the cigar might be better, but basically the takeaway is just having items linked in a meaningful way will help you remember it better. And here's just kind of a trick. I know I put a TED Talk up a while ago, basically the idea of like a memory palace, so relating things that you're supposed to remember, different data, to things that you're representing mentally, your imagery of them, or in this case, a map, and this helps you remember them a little bit better. So this is described, if any of you got the additional CD with the book and you want to go through those labs, this is sort of an experiment that you could do. So imagine sort of a normal path for you to take, could be like the route along the way to school. So that's some path that you would remember, that it's easy for you to remember. Now think about individual objects within that path and relate every one of those individual objects to a piece of information you should remember, in this case, a telephone number. So here's the sort of the walkthrough of the map, as well as the objects that are perceived along the way. Basically, the beginning of the trail that this person is walking, remember the number 9. Then when you get to the baseball field, remember the number 3. When you get to a big tree, remember the number 4, and so on. So this would be the connection of that information that you're trying to remember to things that you would normally see or easily can remember, and that affects or that helps with memory, basically. So it's a technique. It's an interesting technique to be able to remember certain pieces of information. So in summary, mental imagery is experiencing a sensory impression in the absence of the sensory input. Koslin had this sort of idea that imagery shares the same mechanism as perception. So depictive representation in a person's mind, so you're actually seeing the objects, you're seeing the relation in normal space. So things that are a further distance away in the real world are still represented as further distance, or it takes you longer to get to those things even in your mental imagery. First, Peilschlin, I memorized it this morning and it's gone now, which basically shows that it's a dumb name and nobody should be named that. Just kidding. So imagery is based on a mechanism related to language, was this competing idea, and so the debate kind of between the two sparked a lot of research, a lot of things, a lot of studies were conducted basically to prove one or the other one right. In the end, basically, Koslin was sort of the victor, but the dumb name person basically had this prepositional representation in a person's mind. So instead of seeing in your mind a cat on top of a table, you would just have the understanding of the words cat and table, and you would relate them by the word under. So you'd remember that sort of the meaning behind the two things in that preposition rather than the actual visual image. So mental scanning and mental walkthrough techniques are paradigms used in research on imagery. So it's basically that how far away is this thing? If you're imagining something that's further away and something that's closer to you, there's going to be reaction time differences. There are meaningful differences, and that speaks to sort of the idea that it's not just proposition, it's not just words that are connected, it's actual visual imagery. And task knowledge explanations, so that was the Peilschlin explanation, is sort of that you have this pre-existing knowledge of those situations, and so knowing that something is further away, your mind just decides to make it further away. So when asked to imagine something, people ask themselves what it would look like to see it, and then they simulate the stage event. So rather than having it in your mind that way, you're just simulating the time it would take between them rather than mentally traveling the distance. So the flash dot experiment argues against that tacit knowledge, also the Peichlin stuff. So if you remember, it's sort of the images of dots are flashed on a screen, and then there's an arrow, and you're supposed to identify if the arrow is pointing to the dot or not. And the further away the arrow is from the dot affected the time it took for the person to identify if it did or did not point to a dot. So there's parallels that we can see in a lot of studies with imagery and perception. So size of visual field, that's sort of that imagine animals in the distance and how big those animals would be, how far you can walk towards the animals or before they sort of spill over. So again, visual representations within your mind, not just words, not just meaning. So interactions between perception and imagery, there are a lot of studies that are outlined. There's different psychological experiments. So remember the banana on the screen, or priming somebody with remembering or imagining a certain letter and then that affecting their performance when the letter was shown. And there's physiological experiments showing overlap, single cell recording sort of in the brain. So you've got an electrode on a neuron. You also have brain imaging, that lesion creation, the transcranial magnetic stimulation, and real lesion studies that can kind of illustrate the overlap and also the differences between perception and mental imagery. So there's evidence that perception and imagery do not overlap, so that there are different brain regions that are activated for each of those things. And sort of illustrating some of those studies, the dissociation between perception and imagery for sort of the latter half. So basically, yeah, some people think that there's a lot of overlap, some people think that they're totally different mechanisms. And action of imagery can be improved or can improve your memory when you're interacting with these things in a certain way. So there's that remembering things better when they're interacting with each other in your mental imagery, the cigar piano. And then there's also the organization of objects in relation of information to those objects can affect your ability to remember them, so can improve it. Okay, a lot of the boring stuff out of the way, right? Any questions about this chapter so far? No? How about I wake you up? I'm going to show you something kind of fun. 1 second, let me get it up.
Is the test still being posted today, or is that?
Yes, the test will be posted either today or tomorrow, but you'll still have the full week, and I will let you know when everything's up and probably even give you a little more time. And remember your paper, right? And if anybody has specific questions, or I guess I should outline, I think 2 of you sent me a draft of your paper and are waiting for me to critique it. Once I give it back to you, you'll have 2 days to submit it, so don't worry about the deadline and how long it takes me to do things. You'll have time to kind of look over things. Oh, and I guess I should say as well, I'm going to post online, but I'm telling you now, if you do submit it late, if you want to submit it late, you can get 10% off if you submit it within a week. After that, I can't really, after that, it's going to just take too long to get things back to you. So you have a week extra, but you're going to have the minus 10% associated with it. So just so you know. Mm-hmm.
Sorry, I just have a question. If we got, you approved the article a little bit late, you still have till the 14th, right?
If it's past that deadline, yeah. You have to the 14th, and then even a week after that if you want to get the 10% off.
Okay.
So hopefully you guys are obeying deadlines and stuff. It's a bad habit to get into, but I totally understand the needing extra time. So yeah, you can still turn it in late, but you get points off. It's basically like not paying off your credit card and then you have to get the interest. So it's still a small penalty to encourage you to do something. But just remember that, those penalties add up. So try to be good in your life and follow through with things, not just because you have points associated with them or money associated with them, because you want to feel comfortable in your soul and like you're on top of things. That's my speech.
I'm sorry, I'm just like a tiny bit confused. If you sent us like an email or on Blackboard, like we won't get the 10% off if you gave us the extra week because the article.
Yeah, no, you won't get.
Okay.
So you have your specific deadline. You can submit on that deadline for full points or a week after that deadline.
Okay.
Yeah. Yeah, no, it's no problem. I know it's a little confusing. Just with all the time off in the beginning of the semester and things piling up. I know this has been a little odd probably. And so just, we're all in all of this together. So, let me know if you're having problems. We'll try to come up with solutions for you. And we're just all doing our best, basically. Okay, let me show you something cool before we get into other stuff. Okay. So this is Mario. This is an emulated version of Mario. So Mario, somebody cheated and put code online so you can get it basically for free. But be careful, you might download viruses. So that's not the interesting part. Here's Mario. Now I'm going to have I'm going to have an artificial agent play through this Mario game. So here he goes. Here's my artificial agent. So it starts out not knowing anything, and then eventually it decides to start jumping and doing certain things, and it gets smart enough to navigate the level. But I had this going on for, at this point, about 24 hours. And let me show you how far it's gotten. Look at him go. So it started out not knowing anything and then eventually taught itself how to play this Mario level. Yeah, so that's something that can be added in sort of later. So you can see up here this idea of fitness is sort of presented. So it's an algorithm that wants to get the most fitness. All it knows is it needs to get the most fitness. It also knows that going right will give it greater fitness in the level. So it doesn't know anything about coins. It doesn't get any boost for killing enemies. All it knows is it needs to go right. But still, you can see sometimes it dies still. But so this turtle coming up, it dies on that a lot of times. The program will kill it if it takes too long to start to do something else. Let's see. Oh, that one figured it out that it could move forward. That turtle, it died on that turtle for hours, just moving towards that turtle and dying on that turtle, hours. Yeah. Mm-hmm. So you can play it still, yeah. Yeah, it's fun. So I like my agent. I had him going. So this is a, I'll show you the cool thing. I'm just showing off to try to make you a little happier, a little more awake.
Did
you like it? I did not. I found it online. So I got it working from somebody else's online, but the goal is to start to manipulate it. So we solved it. So this one is very hard because he knows he has to move right, but he doesn't know that he's going to keep falling off that cliff. So he's just going to fall off that cliff maybe forever. It might never work. But so you can kind of see all those lines at the top. So it's an evolving artificial neural network. And what it does is eventually it starts making connections between, you can see that sort of that field up at the top left where you have the white blocks and the black blocks. That's all it sees really from this field. So it knows that white blocks are platform and black blocks might be enemies or different things that affect it. So it starts to make connections between once I hit this white block or this black box, then it's going to start connecting it to different game controllers, so like jump or move right or that kind of thing. And so you see the little dots in between are these nodes that would be similar to basically a neuron. So something happens and it either stimulates or suppresses whatever action. So I didn't make it do this, it just did this on its own, and it's totally unique. So somebody else running this algorithm through is going to get a totally unique solution as well, because it just teaches itself over time. And what it does is it teaches itself, and then it takes the fittest sort of things that taught itself, and then it breeds them in sort of a genetic type fashion, so the way that evolution would work. So it's fun. And computer science is cool, and you can use it with psychology, so everybody should be learning how to code. I can't stress that enough. Every person here, probably everybody generally, should start to learn a little bit of how to code, run computer code. Because we interact with the computers all day, every day, and it's only going to get more. Like, we're not going to have less computers. That's my prediction for the future. I bet you'll believe me when I say we're not going to have less connection to computers anytime soon. Unless the world ends, right? So learn how to code. It's fun. So that's basically it.
The world is going to end. We're going to lose all electricity. Everything's going to fail.
Well, hopefully not.
That's what he thinks. He was so ready for 2012.
Like the movie?
Yeah, just like that. He thought that was actually going to happen.
That's funny. Okay, so we'll move on to our review today. So try to get through this quickly. That way we can all ask questions at the end. We'll get through as much as we can, and then it'll be online. Remember that there are videos online, so if you ever miss anything, remember to review it before you take the exam. So the chapters covered in the third exam are going to be knowledge, visual imagery, and language. I didn't approach them in that order, but you have them now or you've seen them. So what is knowledge? What is a concept? The concept of a concept. A concept is a mental representation that is used for a variety of cognitive functions. So I think memory, reasoning, language. So it's sort of that stored sort of file about whatever thing you're thinking about. So you have a concept of, for instance, a cat. You know what to attribute to that cat. So when you perceive a cat, you think maybe it's lazy, it has claws, it has teeth, it knocks things over with its paw adorably if you put a glass of water on the table, that sort of thing. You know how it's going to behave, you know how to behave with that cat. So you have that concept, which contains a lot of different information about the cat. So what is categorization? So the most commonly studied function of concepts is in categorization, so the process by which things are placed into groups or different categories. So how does your mind actually represent the information about concepts? So here's an example of categorizing cars that you see on the street. So you know that the group that you're thinking about is different cars, but then you have the category of SUVs, the category of Chevys, Fords, all those types of things. So different instances of cars are going to fit into these sort of buckets. So there's two approaches to categorization. Comparison approach, you decide whether something belongs in a category by comparing it to a standard in that category. So remember, you have just one thing that you think about, and then you're comparing everything else to that one thing. So it can either be, remember, go back to knowledge, it can either be basically the average of all of the things, that prototypical thing, or you can think of a really good example of what would belong in that category, and then you compare it to that, or a few good things that belong in that category. to decide whether or not this new image, this new whatever, fits into that category. And there's also a network approach where knowledge about categories is represented by different neural networks. So, which are sort of diagrams that indicate how information about categories is organized in your mind. So definitional approach to categorization, decide whether something is a member of a category by determining whether a particular object meets the definition of that category. So not all members of everyday categories have the same features. Remember a chair. So one would know that you can sit on anything and you can call it a chair, but a rock looks very different from a couch, looks pretty different from a seat cushion on the floor, but you know that these are all fitting into that idea of a chair. So family resemblance, so refers to the fact that things in a particular category typically resemble one another in certain important key ways. So you'd know what that key way is. So for instance, I can sit on this, therefore I call it a chair. Instead of setting a definite criteria for every member of a category, the family resemblance approach allows for some variation within that category. So remember, you want sort of a generalizable approach to being able to put things in meaningful information. So we're good at that, and computers aren't necessarily, because we use a matter of heuristics or just sort of comparisons. So you want to do the best job of getting something to fall into that bucket of I know what to do with this. So chairs might come in a lot of different shapes and sizes, but they're made of different, or be made of different materials, but every chair does resemble other chairs in some features. So for instance, I can sit on this. So categories by similarity. So you can, the similarity approach to categorization are based on the idea that membership in a category can be determined by comparing an object to a standard that represents that category. So this approach differs in definition and the nature of the standard. So here's that standard approach. So the prototype approach, that's sort of averaging and deciding if you can compare all the other things to that prototype. Remember that the prototype is not itself a real physical object. It's that sort of average of all of the other objects. So it doesn't necessarily need to exist itself in a set. It's just the thing that you have created, sort of that concept, so that you can compare other things to it. You also have the exemplar approach. So it states that the standard is created by considering a number of really typical things that are within that family. So real examples this time that you can compare information to decide if it fits or not. So prototype is formed by averaging over category members that we have encountered in the past. Prototype is not an actual family member, like I said. And then you have this idea of prototypicality. If something is very similar to the prototype, it has high prototypicality, it's highly prototypical, versus low prototypicality being not that similar to the prototype. This is sort of demonstrating that difference between examples and prototypes. So you have these images of real physical birds. These are examples of birds, versus the last picture on the right is sort of an average of what a bird might look like. So that's a prototype, but there's no real bird that looks like an average of a, I don't know, sparrow and blue jay and middle bird of some kind. I'm not a bird watcher, sorry. So we have this idea that prototypicality can be studied through psychological research. People will find things highly prototypical and can rate them, so you can get some sort of consensus if you ask people to rate on a scale of 1 to 7. So this is a typical type of Likert scale. So 1 would be very similar to that prototype. In this case, we can see that an owl or a sparrow is something a person would easily identify as a bird, whereas a bat is not a bird. It flies, but it's not actually. So it's kind of far away from what is a prototype, what is a bird typically like. Same thing if you have what is furniture, telephone debatable. If it's furniture, it's a physical object that's in your house and you interact with it, but it's not something you sit on or whatever, versus a chair and a sofa is very clearly, very easily identifiable as furniture. You can also, so you can now take objects that you know are very prototypical or lowly prototypical, and you can see that there's differences in reaction time when you ask people to actually identify if they belong in a category or not. So just a little table of the effects of prototypicality. There's a family resemblance, so property of highly prototypical items. In family resemblance, they have more in common with other members of the category. So the more features that you can identify are in common, the more prototypical it is. Typicality, so your reaction time to the statements like a blank is a bird is faster for things that are more prototypical than things that are less prototypical. Naming, people can name first those things that are highly prototypical. If you just say, okay, tell me all the things that are birds in 5 minutes, you're going to first name the things that people rate as highly prototypical. And then priming, I think this is illustrated in a study within that knowledge category, but priming will facilitate making the same different color judgments of highly prototypical items. Yeah, if you remember that, it was sort of identifying if the color presented to you is green, if it's really similar to the thing that you see before or the idea of green, it's going to result in quicker reaction times to it. And then the exemplar approach, in contrast, the standard to which or with which cases are compared is consistent for multiple examples. The exemplars are actual members of the category that people have encountered in the past. Deciding whether a particular animal is a dog involves comparing it to the dogs that you understand in this case, rather than just that average of a dog. It'd be like my friend's dog down the street looks like this. I'm comparing this new dog to that to figure out if it's a dog. Or if it's a rat that's been fed steroids, right? Wasn't that a thing? There were like Mexican fake chihuahuas or fake poodles, and they were actually rats that were injected with steroids. So they would sell them to people, and then they'd find out, this is not a dog. So it's kind of sad and funny. Do you guys know what I'm talking about? Yeah, you've seen it. It's weird, isn't it? Anyway, so which approach, the comparison to the prototype or the example works best? The exemplar approach does not discard any information about the scene. So these things might be useful for later type judgments, so down the line. When you're using actual information versus simulated information, it makes sense that there's less loss and there's more utility possibly associated with it. The exemplar approach can more easily deal with variables or variability in the categories, just because you have different things that you're comparing rather than just that average. So you imagine you have a category with very dissimilar objects, but they're still all grouped in the same thing, such as rather than cars, say vehicles, you have speedboats and dune buggies and planes. What does the average look like in that? Doesn't really make a lot of sense. So having sort of that exemplar approach makes more sense in that situation, that you can say, yes, a car is a vehicle, quicker, easier. But there's evidence that both approaches are used. So humans use both approaches. So the prototype approach, when the first case of category is encountered, so sort of at the beginning of your understanding of whatever thing, if it's not that commonly presented to you, you are going to use the prototype approach more often, and the exemplar approach when more information is sort of available about whatever you're perceiving. So we have this sort of idea of hierarchy we've talked about in the past, but in this case you can imagine, again, like vehicles versus cars. In this case, the example is vehicles versus cars. We also have furniture, chair, table, bed. So you can just keep branching off and coming up with more specific examples for each category that you name. And you can represent these, or you can think about these structures of organization as the top, kind of most broad, being your superordinate, the basic sort of level, which in psychology, that basic refers to what people are typically kind of comparing or typically seeing things as. So that basic level is, a little bit below the superordinate and a little above the subordinate. Subordinate being just another level deeper from that basic. So generally, let's see if there's another. So basically, humans represent that basic level because it's sort of the best of both worlds in terms of your ability to categorize things, but also not too much information, not too detailed that it's still quick enough. So general furniture to specific, like kitchen table, people tend to focus on one level at a time, and basic is typically focused on. Special because it is the level of above which much information is lost and below which little information is gained. So that's saying what I just said in a little clearer terms. In this case, you have sort of that example of comparing furniture to a table to a kitchen table. At the level of table, you have sort of enough information that you can compare it easily to other things. If you gain a little more information by calling it a kitchen table, it's an extra step that doesn't yield you too much utility, so it's not likely that you're going to think of it as a kitchen table versus table. Versus comparing it to furniture, there's a lot more information that you're gaining from calling it a table than just calling it furniture, so you sort of arrive at that middle ground, that basic level. And then when we're starting to talk about the relationship between the different categories, here's sort of a model approach, and think about models as being useful for computer programming. Like I just showed you that neural network, it sort of has these connections and these nodes in it, but here's more generally, you can imagine this sort of hierarchy being that an animal is connected to a bird, and the bird is then connected to those things. So kind of what we saw before in that semantic, in that categorization. So the semantic network is represented thusly. And it sort of gets into this idea of cognitive economy. So you are storing things by their shared properties just once at the higher level node. So things branch off to each other in meaningful ways and easy ways, just to make the most efficient network. So this is in theoretical or in conceptual terms, you can definitely represent this. You can create, and people have created, semantic networks. So we have all that information stored in a computer, but it's just a guess about what humans are actually doing mentally. And there is some evidence for it, so it does take people less time in circumstances to move sort of from one node up the line. So it takes you longer to identify that a canary is an animal than it takes you to identify that a canary is a bird. Just basically that you are traveling up the line, and traveling some distance is associated with more time. So there's some evidence that that works, but there's also, let's see. Oh, here's a little bit more justification for that. So basically, things that are connected to each other in sort of simple terms, you can prime one thing from another thing. So I could prime you to think about ostrich, just in that I'm saying robin, and you go up the line, and you can go back down to something that's very similar. But there's also sort of a problem with the idea of, or let's see, it's not showing this one, but basically remember that the pig example, so the slide of the pig example, it's easier to identify that a pig is an animal, or people are quicker at that than identifying that a pig is a mammal. Even though those are the nodes up the line, there are cases where it doesn't travel up the line. It's just connected kind of randomly to another thing, so it tells you that maybe there's not a lot of meaning, or that maybe this is not what our minds are actually doing. There's also a problem with how do you really get at that in that sort of black box? How do you really seeing how a person's making those connections? So that falsifiability problem, that maybe it's not a good hypothesis if you can't really prove it right or wrong. So in this case, you could maybe say that the link that Randy has between car and fire engine is further down the line, further away than Sandy's, but I mean, what does that really mean, that it's taking you a little bit more time to react? It's just not a very easy, it's not an easy hypothesis to prove or disprove, so it's kind of different. So this is sort of the connectionist approach. So we kind of talked about this in perception, sort of the connection between what's input and then different networks of different, all kinds of different connections, and then some algorithm relating these things to one another. So you might have this idea that a canary, and then it's input in a certain way into your mind, and it goes into all of these different hidden nodes. So it's not necessarily something you're seeing, like you're seeing the input and you're seeing the final perception output. But there's some algorithm going on in the meanwhile, and you can kind of represent that in this sort of visual representation where you can see sort of the dots in the middle. The bigger those dots, the more activation for one of those hidden units, the more it's hitting on that particular algorithm. Again, this is highly theoretical, but basically that the pattern of that activation for those hidden nodes will result in that final output. So it's some wacky algorithm that's responding in a very particular way to input that eventually leads you to that output. So that approach, so the learning process is very slow, but it eventually creates a network capable of handling a wide range of inputs. So I was showing you that neural network. It had been going for about 24 hours, but in the beginning, it didn't even know how to jump really, and now it knows, and it can solve the level more often than not. So the learning process itself can be very slow, but when you're doing this sort of very general way of understanding something, so really complex and structured and precise interaction, it leads you to a better kind of end. So again, or just like think of investment makes sense. The more you're investing in knowledge or whatever, you're getting some output for that. I mean, as long as it's reasonable, whatever. So information about each input is contained in a distributed pattern of activity. So wacky algorithms that you're not necessarily seeing, but it's easier in that case, rather than having direct connections from one thing to another, to have some sort of pattern of activity. It's just a more efficient process. And a connectionist network can represent different concepts by different patterns of activity of those kind of hidden nodes, that hidden algorithms. So the idea of this theoretical connectionist computer science sort of concept, it is neurologically plausible. We know that we have all kinds of neurons and all kinds of connections between them. We know that we will represent information by the pattern of neurons firing rather than just a specific neuron firing. And the idea of this, it's evolutionarily useful because if there's some kind of damage, it doesn't necessarily result in total loss of function. Like if one neuron died, you wouldn't totally lose your idea of whatever that neuron referred to. You'd still have other things kind of picking up the slack, so that makes sense. Learning can be generalizable, so with all kinds of different inputs, eventually you result in something that's better at its job, not specific. It takes longer, but it's better in the end. And it's a basis for successful computer models, like I kind of showed you. So here is a little bit about, again, lesion studies. So visual agnosia, yeah. So different problems with seeing different things or seeing concepts of different things. So these concepts might be very related, living things and non-living things. They're still things, but there's some sort of distinction within our minds, and you can see that when you take these two cases into account. So case of brain damage that results in an inability to name living things, but you're still able to name non-living things, for some sort of injury that results in an inability to name non-living things, but you can still name living things. And there are specific neurons that are stimulated to specific stimuli. So seeing faces versus houses versus Batman, all these things are going to result in a different pattern of activation. So it kind of shows you that those categories are distinct within our minds. You have Luke Skywalker neurons, which is interesting. So they light up very much to Luke Skywalker, but nothing else, or not very much to anything else. So a little bit about how you should study. Think of your basic definitions, the concepts, the categories, etc. So anything that's defined, a lot of times in your book, it's just going to be in bold. So it's always a good thing to pay attention to. What are the approaches to categorization? How is similarity used for categorization? The prototype approach versus the exemplar approach. The effects of prototypicality, high or low, and how you can study that in a lab. Does a prototype or an exemplar approach work better for you? Is it more efficient? Does it result in less information loss? How are categories organized within your mind? What are the different levels of categories, that superordinate, that basic, that subordinate? Why is that meaningful? Why do we even think about that concept? How is it useful to humans? How are relationships between categories depicted? How does spreading activation within a network mean, or what does it mean to spread activation within a network? So connecting all of those points, those nodes and those connections. What does that mean, that kind of concept of that? How is it represented in research? What are the problems with those semantic networks? So remember that pig example, that it's not necessarily easier to follow the line. And you also can't really study that very easily if it's just reaction times to certain stimuli. How do you really distinguish between one case to another case? What are the features of that connectionist approach? What are semantic networks, or what's the difference between semantic networks and connectionist networks? And can there be specific, or can there be category-specific deficits after brain lesions? So that study of living things versus non-living things. I'm going to skip that. So visual imagery. What is visual imagery? This is the last thing we covered. So it helps you sort of gain insights because you can represent information in your mind after the stimulus has gone away. You can work with those different things. You can see non-realistic scenery. You can hear music that's never occurred based off of what your mind decides to activate. So there's no real stimulus, but your mind is showing you as if there were stimulus, or activating as if there were. So it's very useful to you. There are different concepts associated with that imagery. So for instance, the idea that concepts are better represented if they can activate an image. So hat, you think about the image of a hat, and that helps you sort of understand what I'm saying to you. Versus love, there's no real object in the world. You might think of somebody you love, but that concept is not defined, it's abstract. There's some connection between what you're able to do in the physical world versus the mental world. So this mental rotation task, it's not as though you can pick up this image and physically rotate it to see if it matches the example, but there's some evidence that you're doing this mentally, in that it takes you longer to respond if you have to rotate it more. If you have to move it more in your mind, it takes more time, just as it would take more physical time. So here's this island experiment when you are representing visual information. If you close your eyes and you're thinking about this island, it's still going to take you more time to mentally travel from one place to another if they have a further distance across the island, a conceptual island from each other, or that idea of your home state and two related towns. So here's sort of that controversy represented again. So either you have that visual imagery, so that cat under the table, or you have the concept of these two words, cat and table, that are related by the propositional word under. So this sort of the following controversy, so one of the first studies was sort of the close your eyes and imagine the distance between the back of the ship and the front of the ship. So besides that image, you could say that semantically the words that connect these two things have the same sort of feature of distance, and maybe that's what's affecting the time it takes rather than the traveling of the visual image itself. That resulted in that tacit knowledge, so you bring pre-existing knowledge about whatever objects. So it's not that you're mentally representing the picture and that there's a difference between that. It's just that you know, for instance, that it'll take you longer to travel from one end of the state to the other. So it's really that knowledge rather than that mentally traveling the distance that's taking you the more time. So that was a concept, and people argued with it. Here's a study that's sort of pointing out the difference or maybe the flaw in that argument. In that you present a series of X's or dots or whatever on a screen, you wait a little bit, then you present an arrow and ask if the arrow is actually pointing to a real target. If it is pointing to a real target, the difference between how far away the arrow is, so the arrow closer to it versus the arrow being further away from it, results in a difference in reaction time. So it's quicker to respond if it's there or not, if the arrow itself is closer to that object. So it shows you a little bit about, it's not just knowing that the arrow is pointing to it, it's being able to distinguish how far away that arrow is. So there's the size of the visual field, results in differences in perception in the real world. Like imagine there's really a car that's down the street from you versus really a car close to you. It's easier to distinguish the features of the car that's close to you than far away. Same is true for mental images. So you have people think about animals that are very far away, so they're not actually seeing these things. So does the rabbit have whiskers? So in your mind, you're just representing this idea of the rabbit, but there's still an effect if you're imagining the scale of the rabbit as being much bigger than the other object. So the rabbit versus the fly, you're easier to identify that it has whiskers, you're quicker to identify that. First, you're thinking about an elephant and a rabbit. Just as if the rabbit was really off in the distance versus close to you, you're going to have the same mental effect. Same with, in your mind, you represent how close you can get to an animal before it overwhelms your visual field. You have that real physical property that the closer you get, the closer it looks or the bigger it's going to be. You have that same phenomena occur when you're just mentally representing those two things. You can prime somebody with just the visual imagery of some concept rather than actually presenting the concept. So it shows you a little bit more about the overlap in functionality between perception and visual imagery. There are brain regions that are associated with both phenomena, and if you measure the input of a single neuron, you can see that a neuron that responds to the image of a baseball is also going to respond to the idea of a baseball. And if you pick a neuron that responds very well to a baseball but not well to a face, you'll see that both the perception and the visual imagery are going to be specific to that baseball and not affected by the face, and vice versa with the face. You can also see that in an fMRI study, if you are looking at the total activation when presented with some stimulus, the activation is higher when you're seeing it. You also have activation when you're just mentally using mental imagery, you're imagining it. So you still have distinct activation, but it is lower than when you are actually perceiving the object. Again, there are brain regions that are overlapping, so you can really see in sort of, you take that mental image or that fMRI, you take that real physical activation data, and you compare one to the other, so you can think about subtract this thing that we see from this other thing that we see, and if you, just like adding numbers, if 1 plus x equals 0, then you know that x must equal 1, so they are connected to each other in that way. So basically you have this frontal area and this parietal area. You're seeing the same type of activation because you see nothing in the case where you're subtracting them from each other. But in the occipital region, you see a little bit more activation for perception, just because it's in the occipital areas, it's sort of that low-level perceiving of visual information. So it makes sense that it is more active when it's seeing the actual thing rather than representing the actual thing. So it's just a brain region that's more associated with perception. So showing you that there is some overlap, but it's not one-to-one for all regions of the brain. Here's a little bit of more justification that it is, your mental imagery is of the object or the concept of the object itself. When you see that different lesions or different brain injuries would result in differences in the way you're able to imagine things. And you have then, so some things are similar, some things are different. People who have, or a patient who had poor ability to have mental imagery still had the ability to perceive, and vice versa. You had somebody who was able to imagine things but wasn't able to perceive them. So we have a lot of evidence to say that they're very related. Here's a little bit of evidence to say that there are differences, meaningful differences. This just is an image showing you the typical, or the way that information would travel in. So you'd still see activation in those different parts. So it still involves perceiving the thing and storing it in memory for your actual perception. And for your mental imagery, you're then retrieving it from memory and seeing it or having it represented in those, that higher level of visual areas, visual perception, visual imagery, but you're not seeing it for that basic visual input. You don't need an eye to be able to mentally see something. There are differences between, again, that imagery and your perception. So let's see, evidence suggests that imagery and perception are closely related, but the manipulation of mental images is harder than manipulation in visual imagery. So here's a little bit about how you can remember things better, or how imagery affects memory. So things interacting with each other are going to be better represented. It doesn't necessarily have to be a bizarre interaction. Just so long as they're interacting with each other, you're going to be able to remember it better. You can also have a technique where remembering pieces of information with different objects and knowing a meaningful path between these objects might result in better memory. This example with remembering a phone number by relating it to objects seen on a typical path. What to study, what is mental/visual imagery, what does the conceptual PEG hypothesis state, that hat thing, what is the idea behind mental chronometry, what did we cover that? I'll get back to that. So what are typical paradigms to investigate that visual imagery? What's the difference between that Koslin and the Peilschen, anyway. So what is the differences about their concepts and how that sparked different scientific studies? So is it really the spatial Koslin versus prepositional, what is tacit knowledge, and what does it sort of state? That idea that you have some pre-existing knowledge of the thing, so it's not necessarily traveling the mental distance, it's just knowing that it would take you more distance that's resulting in greater reaction time. How do different studies sort of prove that Koslin's theory is more accurate? What's the difference, or what are the neurons, or just sort of remember the studies associated with the imagery neurons? What are typical neuroimaging findings of visual imagery? Are perception and imagery similar concepts? Yes, they're similar. Do perception and imagery share the same networks? Some yes, some no. And how can imagery be used to improve your memory? Again, I'm not going to cover this. Basically did. Language. Language has sort of been a little while from us. So lexicons, these are just some definitions. The lexicon is a word, or all of the words that a person understands, so typically like 50,000. Phoneme is the shortest segment of some speech that would change the meaning of the word if it was changed. So change the I in bit to an A, and you get bat, so it's totally changed. You could also think of SH or TH, so those would be combinations of letters. So it's not necessarily letters, it's that sound or that thing that's that can be swapped. And a morpheme is the smallest unit of language that has a definable meaning or grammatical function. So a truck versus a bedroom, these are two concepts or two different ideas that have definitions. Same as there is a difference between truck and trucks. So structure of words. Words are composed of letters. Letters are perceived and integrated into words. We talked about in perception that feature integration theory. But you also have meaning associated with the words creates some kind of context, so it affects your perception of the word. You have, remember the word superiority effect. So if you are seeing a letter versus seeing a word, and then identifying a letter, you're faster when you've perceived the word, just because we see and interact with words so often that we're just quicker with words, so they're superior. So the meaning of a word facilitates hearing the phoneme. If I cough in the middle of a word within a sentence, you're going to be able to fill in the gap because you know what should be there. So effect of meaning on perception of phonemes. So here's that coughing thing. That's the experiment. Phonemic restoration effect. Participants can fill in the missing of phoneme based on the context. Pre is influenced by the meaning of the words. Following the word can change the way that you're perceiving it. So sort of having that increase in context will help you perceive the word. Perception of speech is top-down modulated. So again, you're hearing the word versus knowing the meaning of it. Knowing the meaning of it helps you eventually perceive the word. So that's the top-down. Speech segmentation. Remember that the physical energy that's being emitted from a word would be very difficult to totally categorize, or it would be very difficult, basically impossible for me to present to you this audio sound wave file, then you to understand what the words meant. But if you're hearing it, it's easy to figure out what it means. Even if you're hearing something that's not the actual words, but just similar to it, you're going to be able to figure out what's going on. So the top row is what's actually being said, and the bottom row is what you're perceiving. So it's similar to that, similar enough that you're perceiving mice eat oats, and does eat oats, and little lambs eat ivy. So speech produces a continuous signal without obvious physical breaks between the words, but our minds are able to make the meaningful breaks between the words. And again, wait, that's the same thing. So ability to segment speech depends on your native tongue versus foreign language. If there's any accent involved, if it's a sentence versus a single word, the context is correct or there's no context, for instance. So all of these things, sort of that top-down modulation, what you're familiar with is going to result in easier identification. Remember, we have that statistical learning. That's the sort of the familiarity. You know how to handle something 9 times out of 10, then presented with that is going to be easier. So understanding words, the ability to understand words is influenced by the frequency that they're presented to you. So very familiar words you're going to be able to identify quicker. The context of however the word is being presented will affect how your understanding will get to that bug versus bug, and the ambiguity of whatever's being presented to you. So that's going to affect it. So in your lexicon, basically you have about 50,000 words. Frequency of the words is related to how often you're going to use them. So if you hear something very often, you're going to use it more often. So response is faster to high frequency words in experiments. You can ask somebody to identify certain things, and the reaction time is going to show you that you are quicker. Here's a lexical decision task in the word part of your lexicon. So you have these 2 lists of random words and basically the high frequency of words. High frequency words are read faster in the list. Again, some reaction time stuff. Also, the context, if a sentence makes sense to you, you're going to be able to understand parts of it a little bit better. So if I present to you that Eskimos were frightened by the walrus, that sort of makes sense because you're associating those 2 things versus a banker being frightened by a walrus, like what's going on here. It's going to affect your understanding of the sentence. It's sort of alarming, like what are you talking about? So ambiguity refers to you're not really certain of how to approach some part of information, but you're going to figure out, or you're going to make an assumption based off of what you experience typically. So if I said to you, my mother is bugging me, you can either assume that she's bothering me or that she's placing secret recording devices around. So those are 2 meanings for bugging, but you're typically going to approach it with what you would typically assume. You can also prime somebody. So presenting a list of things and then saying an ambiguous word when it's associated, when you have more context for that situation, even if you're not presenting the concept of ant, that was never presented, but the concept of bugs is presented, so it resulted in a priming effect, so quicker response. So letters in words, or letters and words, we can segment speeches up based off of our native language. It's easy enough for us to do this. So to come up with individual words and individual phonemes that we have within those words, it's just sort of natural. Our brain allows us to do this. And then remember that if I cough in between something, your brain's going to be able to fill in the gaps easily just because that's what you're typically presented with, as well as if I present to you a word and ask you about a letter in that word, since you're so used to seeing words, if I ask you about a letter in contrast, you're going to be faster at telling me about the letter if it's presented in a word versus on its own. If something is ambiguous, let's see. So anyway, frequency will affect how easily, how quickly you're going to perceive a word. If it's presented to you frequently, you'll be quicker at it than if it's not. So meanings are assessed for ambiguous words. That's sort of that bug and that priming experiment. So let's see, the elimination of lexical ambiguity, the context that's presented sort of afterwards will help to eliminate the ambiguity that you're experiencing with that word. And you can prime somebody with that type of experiment. So the context provided by the sentence will help you understand the other words within the sentence. So there are 2 properties of sentences: semantics, so the meaning of the words in sentences. There's the syntax as well, so the rules for combining words. And there are differences sort of in brain activity. So if I present to you something that is semantically odd, so the cats won't eat versus the cats won't bake, you're typically going to see cats eating. Why would a cat be baking? So it results in different brain activation. And then differences in syntax, so the way that things fit together. If I present the cats won't eat versus the cats won't eating, you get different activation because you know that there's something odd about one of those sentences. Parsing refers to the way that you're splitting up sentences, and there can be ambiguity in the way that something is presented to you. It's the actual physical words or the way that I'm presenting doesn't give you the information, but your mind's going to make assumptions about that. Let's see how much I have left. 88. Yeah, I'm not going to finish. So I will post these slides, and then I'll just post the rest of the video later. So email me if you have any questions. I will post the exam either today or tomorrow, and you will have over a week to complete it.